Okay, so welcome to the third day of the Masterclass. Today is Adrien, but this morning, this afternoon is Adrien and me. So Adrien is from Aalto University, Finland. He will talk about parallel computing state space models. So we'll probably have a breakdown plan here. So whenever it works. Anyway, whenever it works for you, yeah, you can just go and break whenever you want. So yeah, we can start whenever you want, Adrien. Yes, I do.
Yeah, thanks for having me. So like what we've been seeing so far has been like somewhat on the technical end, so like programming and maybe like hardware. I'm going to be talking a bit more about the methodology, and specifically I'm going to try to insist on what parallelization enables, what it makes hard, and what you have to kind of be careful about. Right. So that's essentially what we're going to be talking about, and we are going to be doing so by focusing on state space models for two reasons. The first one is I think it's actually a fairly nice thing to see how you can parallelize them, and the second is I have done research on that, so it's a bit easier. So like with my. Okay, so first of all, like some motivation and background, specifically about state-based models. So what we are thinking of today, or this morning at least, is models of that form. So you have a dynamic, so like a fundamentally Markov kernel, and the Markov kernel is observed or like is kind of equipped with a potential function across all time steps. Now, in general, that looks like that. Right, so just a Markov chain, so like Markov kernel and initial distribution, and then there's some potential function across the time steps. You have like different instances of that, so like when the potential is Markovian, essentially when it splits across time steps. When it's separable, and then like if you have an observation that corresponds to a state space model case, which is probably like how it was originally thought of. Then like you have also parametric versions. So like instead of just learning to infer the latent state, well, instead of just inferring the latent state, we also want to infer some parameter of the model. And then like interesting special cases from arise when we have conditional Gaussian dynamics, or even better, Gaussian dynamics. Right. So in practice, what we of course, like you have the linear database case, which is like Gaussian dynamics and Gaussian observations. So in practice, what we will be talking about mostly is Markovian, right? And a specific instance in terms of the state-based model, and also about Gaussian latent dynamics and Gaussian state-based models, right? I'm not really going to be talking about the general like potential that is across all time steps, but it's also something we can treat speak. Right. So here is like the general smoothing, filtering, smoothing problem statement. So you give yourself a state-based model that we can set like initial distributions or observation distributions, but depends how you want to call them, and some dynamics, and then like you have essentially two sets of problems. The first one being the filtering one, which is about trying to understand the distribution of the state, even all observations seen so far. So that is something that's very useful in the online setting, right? So like when you accumulate data and you just try to kind of like infer where you are as you go. Think like target tracking, people in the moon, pick it up. That sort of thing, right? And then you have the smoothing problem, which has two instances: the marginal smoothing, which corresponds to trying to understand the time step and even more observations so far on like think of state support at least, and then like the full pathwise smoothing problem, which is the one that we are going to be looking at a bit further today, which corresponds to trying to infer the full post-edit distribution of the code. Right. Right, and so the way you kind of do that is by Bayesian methods. And so like the first one we want to look at is the Bayesian filtering method. And I'm going to be talking about like the sequential, but I can go to the parallel version later. And so the filtering procedure, Bayesian filtering procedure, is essentially a recursive method, which corresponds in which essentially consists in which consists in saying that you know the filtering distribution at time t-1, right? And you just want to kind of compute the predictive version of that. So kind of like what would be the predictive distribution of xt given all observations up to time t-1. And that's kind of fairly easy to do, at least like on theoretical, at least like algebraically, right? You just integrate the predictive distribution. Yeah. Yeah, because like that completely collapses. Yeah. So so you integrate the distribution with respect to its margin, right? So you just look at t-1, right? It's just the integral of pi of xt, xt-1. T-1 and the p of t-1, right? T-1. Great. Yeah, that's basically just that. Sometimes it has a plus one solution, sometimes it doesn't. And then you apply something that people tend to call the update step, which just reincorporates the observation at time t. Right? So you get the distribution, then you get the observation, and you just correct for that. And that's just like basic. All right, so what does it look like? Finite space-based models, those integrals become sums, right? And so your distribution pi of xt is essentially just pi of xt equals pi x4. Or a number of sequences. And so now like the predictive is just the integral of the transition against the filtering distribution at t-1. The update itself is kind of the same thing, right? So you just multiply by the likelihood and then you normalize that. Okay, leaving that there for like a second. Just give that. Yeah. With Gaussian, we also have closed-form solutions, right? And so the predictive distribution is now just applying a linear function to a Gaussian. And we kind of know that it's still a Gaussian, and we know the mean and we know the covariance, right? Affine. And the update follows essentially from Gaussian algebra, right? So like you just form the way you prove that you form pi of xt, yt, given everybody, right? So you form the joint distribution and then you margin that. That's just like bachelor. Right. So the Bayesian smoothing itself is kind of like trying to go back, right? And it's also a recursive formulation. So you say that you assume that you know the smoothing distribution at time t, right? And you just try to go to t-1. And so the way you do that is essentially by a marginalization network. So you have you have the smoothing distribution at time t+1, right? And then you just integrate the smoothing distribution with respect to that. So this essentially looks like pi of xt given yt is pi integral xt it so t plus 1, and then right. Just to think of it. Makes sense so far? Then you just like manipulate a bit the terms, and you apply Bayes' rule, and the final instance is that one. Right. The pathway smoothing distribution kind of follows from the same step. So instead of like thinking you make a marginal at empty, you just say I know the future. Right? And there's not much difference in that respect. Because this integral that arises is just for the marginalization so that you forget about x plus 1. So if you don't want to forget about it, you can continue to integrate it. Right, so the instance of it in terms of the finite state space case kind of looks like that. So you just end up doing some matrix multiplications, right? And then like normalizing that distribution. The pathwise one is a bit more painful, right now at least, but like that's something you can implement in fragments. In the case when you have a Gaussian, you have the same type of structure. The equations are a bit painful to derive, but they essentially follow from the same Gaussian matrix. So you form xt and xt plus 1 together, given all the tasks, and then you either marginalize or the condition. Right. Pathwise smoothing, it's not too hard. I didn't have it. So yeah, so those two methods are essentially sequential methods of deriving the posterior distribution for the space-based model or fragment cap model or any kind of latent dynamic model that you might be interested in. They are, because they are recursive, they're sequential. So you do like predict, update, predict, update, and you do that time step over and over again for any time step you're trying to complete. And then to do the smoothing, you do it backwards, and again, like you just go back and so time step. And so those methods are sequential, and essentially they are optimal for processes that are sequential, right? And data that's writes sequentially. So if you were to do like something online, you get data. So typically people think of data as data, like weather prediction and kind of stuff. This would be the optimal thing you can do in terms of compute. Like just treat it as it comes. But if you already have your data and you're trying to understand the smoothing distribution, it might not be the best thing you can do. And you can think, okay, maybe I can just treat the whole data set at once, right? Rather than like treating it sequentially. And that's essentially what we're going to be trying to do.
Sorry, just a clarification. Smoothing distribution, you cannot do it exponentially. No, online, right? Once you have a new data point, you have to recompute.
No, I mean, there are ways. There are ways to do it online. The person right behind you is probably the right player. But I mean, there are ways to do it to compute smoothing expectations online, especially when they split across time steps. So when your test function of x0t is actually just some over time step of xt and xt plus 1. So for example, the scope, right? I think both are important. You have them nice.
Okay.
But yes, like there are always strategies to compute the expectations, like getting samples from it online.
It's hard to get samples of that online, so you have to update state that for the backend file.
Yeah, I'm just assuming that maybe the Paris people might tell you otherwise. Because that's kind of the promise, but it's
That's impossible.
yeah. So yeah, like you can't really do it. So you can do that online, right? But that's basically what it stops. At least for particle filtering, I think with Gaussian is not accessible. You can't really do it. Right. Okay. So the reason why we want to treat data non-sequentially and like parallel is essentially because of hardware, right? So we just look at our hardware and we say, what do I have in there, right? So my CPU maybe has like 16 cores, or less. So it's laptop. My GPU is going to have like 5 6 of them, right? And that's just a standard like commercial laptop. If you look at computers that you can buy, actually it's very cheap for academia. It's like 10,000 for like a massive computer. You end up with at least like 2 GPUs with a 10,000 CUDA cores to like processors essentially running on them. Was like the best CPU you can think of is going to have like the order hundreds, but I think that was very best. Course. I think we want to have it work as like 64 cores. This as well. Very good. Right, and so like based on that thing, we just want to try and like get the full cluster distribution of state-space models, Feynman models, but like in parallel, right? And something we actually want to be very careful about is to manage to process things in parallel in a way that is statistically friendly. So we kind of are happy to read a bit of precision, like increase the variance of our estimates for the sake of getting computational resources, right? But not too much. So we're going to try and like see how we can do it. Okay.
Thank you. Right. So that's a quick question, just a clarification. When you say high dimension, you mean high dimensional instead of
I mean both. I mean both. Yeah, I mean both. In fact, weirdly enough, the high dimensional case is more suited. Like the high dimensional is more suited because the observations tend to be highly informative in that case, right? And therefore, the sequential, if I'm thinking like particle train sequential version of it kind of collapses to the parallel one. And so like you're not making any error by like localizing stuff, by utilizing time stuff, or you're making less error than you would if you had something that was more trial, more dynamic informative than like yeah. I'll point at it. The transcription is like really great. Yeah, but I'll just point out from them. Okay, so the actual outline of the lecture, right? So we're going to be talking first about prefix sums, so cumulative sums and the applications to essentially exact, approximate, and Monte Carlo exact inference, right? So I mean, it's all there. It's kind of been touched upon a tiny bit over the past few days, especially by Dan, but there's going to be a bit more details here, and I will be answering your question about. So the second thing we're going to be looking at is the parallel resampling in the particle filter. So it's going to be the parallel sampling. So the first one I have like I have some stake in the game, so I have worked on that. The parallel sampling is like mostly going to be based on the work of Anthony Lee, Laurence Murray, and Ken Jacob, I think those. And it's going to be a bit more freestyling. So like we're going to look at their method, and we're going to try and see how it can be extended, how you can try and like think of it in different ways and make in the future work. And then the last one is probably the one where I put the most yeah, that's like a very intensive subject of my research, which is like developing methodologies for smoothing in that case. I also point out that it's not only for smoothing, but that I'm treating the smoothing case because it makes the whole thing great. Right. Okay. Questions so far? So prefix sums. Prefix sums. So as we said, prefix sums are essentially a form of cumulative sum, but for operators that are associated, right? So in general, like if you just try to think of a sum, you kind of not. So you say, I want to compute my given data I already have stored in memory. I want to compute the cumulative sum thereof, right? So what you typically need to do that in parallel is monoid, but if you want the informal definition, you just need that capability and you just need the zero element. And you don't actually need the zero element. In all the generality, like you just give yourself an operator. Just like formulation. Right. So if you were to compute a parallel sum, right? To say I just want to compute a sum, then you would like probably all of you would just like go with that solution first. Like I just write everything down, then I put my parentheses, 2 elements by 2 elements, I compute those in parallel. Then I just collapse the 2 elements into one, do that again and again. I like the standard divide and methodology. Right? Assuming everybody's performed. Next one is a bit more like it's a bit more complicated in a sense, but actually it's simple. So if I wanted to compute the cumulative sum, what I would be doing is I would essentially be computing partial cumulative sums as I go. So there are like 2 algorithms. I'm just presenting the simplest one. But so you say you just look at your data set, right? And then like the first element is left unchanged. You just know that. Then like the second element, we just add x1 to it, and we just replace x2 by it. Right? X3, same thing. We just look at the previous element, and then like we just look at the cumulative, the sum, the partial sum between 2 and 3, partial sum between 3 and 4, partial sum between 4 and 5, and so on and so forth. Now, like the third line, I know that x1, x2 is going to be left unchanged, right? But the x2, x3, I'm just going to pretend x1 to it, right? Now, x3, x4, I know I'm going to have to pretend x2, I do it. x5, x4, I have to pretend x2, x3. So I'm doing that one, right? I'm pretending I'm just adding everything as I go. And then like the last line, I just combine what I have left. So you can kind of like convince yourself just via the out.
It's not parallel, right?
So what you do is each operation that happens at each level is parallel. Right, so
going from one row to the next.
Yeah, you're going from one row to the next, and each of like every operation on the same row is parallel. Okay. Okay. Makes sense?
Yeah.
What are the data?
It's essentially like the copying and you're just kind of like moving the data to be able to do validation.
All right.
I mean, you're not moving it, but you're accessing the partner, accessing it, and then adding the data to it. Yeah, but everybody's kind of convinced that you can generalize that to any data sets of power of 2. Right? Okay, if you don't have the power of 2, then like you can either like just add, right, with your 0 element, or you can kind of like manipulate data so that you can actually that. Right. Okay, so
And how many steps does it take to do it?
log what?
Log.
How many? Yeah, and we have like 8 elements, right? So you take about 2, and it's kind of easy to see because like the number of operations you need to make divided by 2, right? So here, like at the beginning, you're making 8 operations.
Yeah.
Right. Then like the next one is 4 operations. Then no, it's no, it's not 4 operations, but it's you're summing like elements 4 by 4. Right. So like you go 2 by 2, 4 by 4, and then 8. So
And to compare to the previous approach, where you just split like you just pair.
yeah, okay.
How does it compare?
Good point. Yeah, so by like memory-wise, you see like once another completely different.
I assume you're reading first, right?
No, you should fix.
Oh, yeah, that's okay.
But so like here, what you can just like grab the last element, and that's a sum.
Yeah.
Right, and so that's kind of like how you could also implement your documenting. So the main thing big that at least that one is going to be Dan, do you know if it's better in terms of like memory allocation to do the tree structure or to do like with operating sum to get the full sum?
Yeah, I haven't studied the time complexity, but yeah, in terms of linking it back, you are just propagating up the binary tree, keeping track of all the partial sums. Then you can propagate back down, keeping the cumulative sums on your way back down. And personally, I find that an easy way to think about it. And it's clear that then it is 1 or 2, but
the algorithm you're talking about is the playlock. So it's the upsweep downsweep.
Yeah.
Right. This is a different algorithm. But but yeah, you could just do the upsweep and then like this remove the downsweep to do because you already have the last element as a book.
But if you just do the upsweep, you don't have all of the cumulatives.
No, but you have the last one.
Yeah.
So if you're just trying to compute the sum,
Yeah.
oh, that's already
Well, that's it. Yeah. So yeah.
I'm actually not sure. Like, if you just want the sum, if there's a better way than that.
Okay.
Maybe.
I have a slightly related question. It's not exactly in this scenario, but you know that when you have multiple matrices, there is also an associated operation with them. The way that you remove matrices may have different cost when you can put out a matrices. So do you have any influence in this case?
I didn't understand the question.
Yeah, so if you have multiple matrices instead of so here you are considering like numbers, you are considering the sum problem, right? You have number that you might work with. So
No, I just have an element and associated.
yeah, but it has matrices.
Yeah.
And even in the sequential case, the way that you remove matrices may have some impact on your computation of course.
Yes. Yeah.
So are you aware of any way to combine that with the variable or equation of the product matrices?
But the product you're always going to pay in increments. So I don't really understand how that.
If you have matrices of different shapes.
Different shape, maybe. Okay, different shapes.
Yeah.
Different shapes. I'd be surprised if you could do that.
But it illustrates the trade-off, right? So the classic one is you got a bunch of square matrices, then a vector at the end, like the Jacobian calculation, right? Obviously, it's easier to sweep back. That's why reversible form is better. But if you want to exploit the parallel hardware, you're going to pay the price to multiply the matrices because that's the best way to exploit the hardware. It's not most efficient in terms of total number of blocks, but in terms of block time, it's still very better.
What do you think the different shapes have to do with it?
So I think what the different shape can influence the performance in the sense that the way you, so here for instance, you say you group is one is two, three some. I mean, it's zero or it's five or six, then you have no problem.
Okay, I got you now. So like kind of Einstein optimization.
Yeah,
Like Einstein summation optimization, just to get the path of the summation that minimizes the number of operations. Now that's not problem. Like you wouldn't be able to do that in here. No, you just wouldn't be able to. There are just probably better ways to do it specifically for matrices.
Yeah, I think there's a reason why you apply the kind of Einstein optimization that you have mentioned, and it's moving to the reading information. I haven't seen anything like that.
Now here, just think of the elements as being homogeneous, because that's what we're going to do anyway. Right. Okay. Is anyone allergic to dark mode? Right, so like essentially like a sequential implementation of the algorithm we have. It looks like this, right? So you just get your array of data, right? Here, like the operator I'm just looking at is the plus operator, right? And so you just iterate across log number of elements, right? And as you go, you just try and like implement those arrows we were seeing, right? So you just point at the element that's to the power depth to your left, right? And you add it to yourself. Okay, and that's basically it. Now the thing is, that loop is inherently sequential, right? And so you can't parallelize that. You have to pay the cost. But that one, all those operations, they are actually happening on elements that are separate, so you can fully parallelize that. All right?
Just to be clear, this is for the cumulative sums?
This is for the cumulative sum, yeah.
Thanks.
So like this specific array is going to get how to cumulative. All right. There is like another version that is the one that Darren was alluding to, which is, in my opinion, a bit harder to explain. So it's probably easier to implement to some extent because like it doesn't have that problem of having a number of operations that varies over time. Like like in the algorithm I have, like depending on the depth, you get a different number of operations to apply. That's not the case of that algorithm. And it also happens to be more work efficient. So the total number of operations we're going to make here is actually commensurate to the actual size of the array. Right? The total number of operations you do in that one is n log n. Right? So you're making more operations, but in exchange what you're getting is that one is more parallelizable. So here we have log n, number of steps that are parallelizable. In that one we have that twice. Right? So like you have different implementations with different properties, and choosing the one you want is essentially depending on your output. So something that people think of is if you have a ton of cores, you do that one. If you have limited parallelization, you do the second one. Right? Because it requires less operations per lane. Those are just test and if you were to use JAX as something I want to, yes. So like here, like the total number of operations for the first version versus the total number of operations for the second one. Right? And you can see like the work efficiency kind of happen. If you are to do JAX, then like the prefix sum operator just has that associated scan, right? And the way you use it is you give it an operator and you give it data. And then it just computes the cumulative sum of your operator on your data. Here, what I have is like I did some Python magic to kind of like count the actual number of operations that were happening in the just computation. But you can see they are better. Yeah, there might also be some additional things that are not considered the visualization itself. Because yeah, just work out on the additions. Right? And you see like the syntax is not too hard, so it's something you can use fairly very hard. Yeah. Questions so far? We're going to be using them quite a bit, so it's good. It's good if everybody is kind of comfortable.
So Jax is using the second one.
The second one.
The second one, the number of computers are less. The reason is that why is 26 now?
Instead of 30.
Ah, okay.
Because my implementation had 30.
Yeah. Okay.
And the reason is just because I'm not an efficient. I just coded it like the quick and 30 to kind of straight forward.
Okay.
That's the main reason. Yes, it's the second. The reason being that's like so if you think in terms of pure JAX terms and not really in terms of GPU or anything, the first one, if you want to parallelize the operation, you're going to have to apply a function, right? So you're just going to be doing f on some array, right? But the array size changes with the number of iterations you're doing, right? And if you're thinking JAX, what happens is that they compile a new function every time the size of the array changes. So that's actually very inefficient. But this is like a pure JAX problem, right? If you want to do something in pure CUDA, the second one doesn't have that because the number of operations you're making does not change. Any other question?
We don't need to get stuck on the details, but is there a name for the second one if we want to look at?
So the second one is the Blalock algorithm. The first one I actually can't remember. Is the yeah, the first one is the easy to explain one. That's the name I give it.
Okay.
Yeah, the second one is Blalock. I think Blalock has the two algorithms. Something somewhere like in the 60s. Okay, so now that we kind of like understood what replacements were, hopefully, we can try to see how, well, we will see how we can apply them to the filtering problem, right? And so I'm going to be looking at the object, the filtering object, in a theoretical framework first, and then we're going to see its instance in the context of Gaussians and finance database models. Make sense? Yeah. So this is the modeling concept. Right. So we consider elements which are essentially Markov kernels, and they are normalizing constant. Right, that depends on X, or at least something proportional to that. Okay. And then we consider that operator. Okay, so what is it? What is that? Okay, does anyone have like an idea of what that can be?
Like yeah, it's like this moving stuff.
It's a form of rated Chapman curve. Right. So you have the two transitions. Right. You have the two transitions, and then you have the weight function. And so like you're essentially doing a Chapman curve graph, so like like a marginalization with respect to the intermediary step. but you're weighting it out by that potential function h. Yeah, and the h function is just like how you also propagate that. Right? So proving that it's associated is a bit painful, like most computational exercises. But the second one is fairly fast, so let's do it. Let's do it. So I have my h I, h j, hk, right? And I have h I j, right, which is written like that, and then I just want to compute h I j, which is h I j. I'm just looking at the partial version of the operator here, and h k, right? So this is this is h I j x. That's an x. Okay, that's an x. And then integrate y hk of y and f j of y x, right? And so this is x integral integral I x, right, and then and then you just move around. Right. H. Shape one. This you get as well, so that's why I'm
The formulation of Fij does not depend on Hi.
the Fij does not depend on HI, correct? Yeah, correct. Because you're using the weight in your Chapman tomograph comes from the second one. Fi dy x margin, and then like the numerator is also given there. And so the only thing that's magic is this. Sort out, and then they get say UTF is for the potential.
Is in principle, is there a way of doing it without separating the F and H, where you just have an unnormalized color through, or it's there's more
Yeah, the smoothing is enough. So we'll see it in the smoothing case. You should try that. On the roll because it's taken.
Yep.
So this is just general version. And so if you want to do that filtering, you just need to first like enumerate the elements that are going to be in your initial data set. So we want to compute this. Right? What are the initial versions of the elements that we want to have so that the solution is the filtering solution? Okay. So at each index of the filtering sum, what we actually get is the filtering distribution at the time step that we are looking at. Okay. Well, it's kind of like just dropping the formulas here, but what you're looking at is the predicted distribution for an step. Right, and those are essentially your elements. So F is the predictive convolution model of xt. Right, so it's xt given xt minus 190, and then H is its normalizing constant. Right, it's just yt given xt minus 1. All right, and then like the zero element is just like initialization. doesn't really matter. It's just something that doesn't impact xt minus one, or in a sense, it depends on some spurious variable that hasn't. Yeah. Okay. When you've done that, and when your elements 80, which were like those Markov kernel and their potential, like their normalizing constants, when I call them A, and I apply the sum on them, then, sorry, I just apply a sum on them. What I get is the filtering distribution at time t, and then the marginal likelihood of the observation, so the normalizing constant. Okay, it's kind of like it's a fairly easy exercise. In fact, like you can just do it by version, like by induction. Yeah, you just do by induction, right? Because we know that the method is associated, and so any way we manage to make the sequence happen is going to be the right way. Right? So you just say, well, let's assume it's true at time k, at time t. Let's assume we have it. By t and t by t. And then like let's just write 80 plus 1 as what we had, right? So p of xt plus 1, xt by t plus 1, and p of by t xt plus 1 xt. That's our element. And then we just apply by t p times and x. So the transition is a bit painful as always, but like you have integrals, but that's the marginal likelihood is very easy because it's just we're just looking at so p of t times integral t by t plus 1 xt t of x t plus 1 xt by t plus 1. Right, dxt plus 1.
Yeah, think
I
you need an xt.
now there's just I forgot them down, and then you just write writing on by hp of x minus 1, which is this.
Why plus 1 to the xt?
Right?
Yeah, I think so.
That is what's right.
It's the normalizing constant of what's upstairs. It is the normalizing constant of what you have upstairs, so I think you should be okay.
So now you just integrate with respect to that. I just not integrate things with respect to the right thing. Yeah, I mean, like that. But fundamentally, just reformulate right. If you want to give it a try, rather than like thinking in space-based models, you can get playing on that models and see how the equations vary.
So let's make it a little bit simpler. If you do not have the potentials at all, and you have just Markov kernel, And what will you become?
I have,
You have no potential.
they have potential of one.
Yeah.
And therefore, like, you just get the standard champagne from the world.
Right. That's an unbelievably.
And so along the same lines, the identity for the dynamics is just doing nothing?
It's just confusing the
No, sorry, the identity element.
Ah, yeah, the identity
Stay where you are.
is the diarc. Right? Xt minus 1 ext, and it's 1. So that's your 0 input. Yeah. That takes much too. So what does it look like? So when we have the finite space-based model, all we kind of need to do is to instantiate our elements, right? So H was just the predicted distribution of the observation, right? And F was the predicted distribution of the 15. Sorry, I don't know how to call that. So one step filtering distribution of X, right? And so you just write it down like that. When you look at the actual operator itself, right? You can get this can translate all the integrals. And so the magic is that's implementable. Right? If I give you well, transition matrices, which are these. So if I give you transition matrices, right, and I give you emission likelihoods in the terms of hidden Markov model people, then like you can implement all that. Okay, and if you can implement it, and especially if you can implement it using a finite amount of computational resources and memory, then you can just replace some things. Right? And so we have a way to parallelize filtering for agents, and that's already something we have right now. Right? Okay? Everybody happy with that? Right. So if you want to play with it a bit, that's also what I said to the slides before. We have some notebook. I'm afraid it's in TensorFlow. I'm afraid it's in TensorFlow, but the method kind of is all implemented in there. So you have like the standard, like the natural implementation, and then you also have the block space implementation, which is how you need to do it to be stable, because otherwise it's just a bunch of applications and we all know like this. To kind of show what it looks like. So on the CPU, right? On the CPU, you can kind of already see the speed up, right? So even though like we don't have that many cores, because I think that is actually run on the local lab, so like the CPU is not great. You already have the speed up by using the prefix, right? And it's probably because the HMM is not big enough that the parallelization is happening at the time step level rather than the XM level. But you already have something that kind of works well. And when you're looking at GPU, then like it's a complete victim, right? And so I think yeah, that's the number of data points. So this is like hundreds of data points. I think the state space is like 50 states, something like that. It's a fairly small HNF, right? But it's still like a fairly realistic example. So it's still like okay. Questions about that? I mean, like, no? So if you want to go play, it's I mean, it's there. Right? You can go and see how it's implemented. You haven't used it. Right, it's like different. So you would have an operator which is essentially just a function. So we can just function. So that's essentially how you would do it. So this is like logarithmic matrix vector multiplication, right? And so it's just saying, let me get my log transition matrix, well, my log this transition matrix, just like the one that we have on element. Let's take its normalizing constant, and let's just do our operations in the log space. And you can see that it's 5 lines. Once you have that, you need to understand how you initialize everybody, right? So it's kind of like the definition of the elements we have. And same thing, it's essentially 4 lines of code. And once you have all that, you just get your initial elements, you apply the associative scan on your initial elements using the operator, right? The specific max number of levels is to help TensorFlow with the calculation. If you don't specify that, they simply go a bit too far. It's not a team, and it makes so that it doesn't really matter. And then you just gather the filter solution. Right. So what are we talking about here? Like we're talking 20 lines. And so we do the Gaussian case, and then we go down. Yeah. So the Gaussian case also happens to be implemented. So the main idea is to just parameterize the transition and the normalizing constant by the transition matrices, the offset vector, and the covariance matrices. Right, and so you say that your potential is proportional to Gaussian. That here we write down in the information form. So the information form is if you have a mean and the covariance Q, then the information is Q minus the information parameterization is Q minus 1 times mu and Q minus 1. So you look at the precision matrix and then you scale the mean by the covariance. So
this is like what people would call the natural parameterization for the exponential family. It's not the same.
No, it's like
yeah, no, I think it is. I think it's what I would call canonical parameters. Very good.
Yeah. No, I mean it's not the canonical representation of the exponential family. That I.
Well, it's the parameter that add when you multiply the densities.
Yeah, right. If you're thinking of like the exponential family canonical representation, it's not the right one. So that it doesn't run into statistics. That's in that sense. Just think of it as like form of final relation. So yeah. Right, and then you just look at your transition density, and you just say, well, I'm just going to take A, U, and C. Right, and so my elements are now eta, J, A, U, and C. Okay. So now that we have that parameterization, the only thing we need to do is to compute them. Right, this is just Gaussian arithmetic. It's like we know them higher. Right, so that will. Sorry, that one we actually don't need to compute it. And then no, it's actually pretty bad. So F T xt minus 1 as a reminder is P of xt xt minus 1 and y t. Right. So it's not directly the ones from the model. You just have to kind of compute them from that. It's just a reminder of that. Right, and your identity element is at the bottom there. The left. So identity transition matrix, 0 offset, and 0 covariance. It's a diagram. Okay. So now, like you do your Gaussian algebra, and it's a bit painful. But the reason why I'm showing that is to show that it's implementable. Right? So it's just a number of making verifications, inverses, and that's basically it. And same for the operator. Okay, so you just just get on the value of the method and that's what. So same thing. Same thing. So here, like yes, also. So the it. So here, like it's a bit more painful to actually define the elements, right? Because it's in algebra and takes some lines, but it's not complicated. Then like the actual operator is going to look like that. So you take A, B, C, J, beta, and then you apply the iterations that correspond to this one. And you return it. Now, an interesting thing that you're seeing here is that G-map, right? And that's only there because associative scan just takes something that is vectorized in the sense that like, it requires you to be able to apply the operation as a batch or as a set of elements. Once you do this, then you go down and you just realize that in the context of Gaussians, then the parallel version works more fully on the CPU than the sequential one. And the reason is because Gauss is actually pretty bad at CPUs. As an FYI, it's been optimized for GPUs and specifically for TPUs. So it actually doesn't really handle multiple processors, CPU as well. So contrary to that approach, which is why we have an improvement in this way. On the other end, the parallel version just well completely beats the sequential. And this is like also a fairly natural example, and I think it's 10,000 times faster. So it's just beats it all possible. Yeah, in fact, like that was run on Corenflos, right? And so if you used a proper GPU, not the free version they have on there, you will see even better.
It's very important. You scale your I and Y axis by the scale, and you have two slopes that are different. So,
which ones?
Okay, let's say the sigma.
Yeah. So the
price suggests that is
so the sequential algorithm,
yeah,
right, is O of n. The parallel one is O of log n.
Okay, that's fine.
Yeah. That's the whole point of the parallelization. We want to make like n operations happen in log n time. Any other question? And then good.
Hey guys. Be back in 10-15 minutes. Yeah.